So last time we ended with an example where we did an area between two curves with two different approaches. And so what we kind of developed out of that is as you're looking at whether or not you should partition along the x-axis or along the y, there's a couple of things you want to look for. But really kind of the heart of it is looking at, so if I partition along the x-axis, our little representative rectangles that we draw, if the top curve always stays the same and the bottom curve always stays the same, then we probably gravitate towards functions of x. So here, partitioning along the x-axis would make the most sense. Now, on the second one, and let's contrast that with if you had partitioned that and you were to think about, well, what about if I did it with functions of y? Then it would change, right? Because you would have your curve, notice if you partition and you do right curve minus left curve, you have two different curves that you would have to end up setting up more than one integral here. Two integrals is what you'd end up with. So definitely in this case, functions of x would be the way to go. All right, on the second one, if we think about partitioning, using functions of x kind of along the x-axis, functions of x look good. Top curve and bottom curve stay the same throughout. And that's probably what we gravitate towards if given a choice. But depending on how maybe the functions are given to us, what if I'm working on this example and the problem just so happened to give me these solved as functions of y. So x equals, functions of y. Well, here it would be fine to partition, I think, along the y-axis as well. I would probably make my choice more just dependent on how the functions were given to me. Because here the right curve and the left curve always stay the same, so still just one integral. But when we get to the last one, this is a lot like the example at the end of the last video. Because if we try to do what we more naturally, gravitate towards, top curve here as a function of x would be, probably that square root of x, and then my bottom curve is going to be that minus square root of x. But then all of a sudden it changes because my top curve, as I move over here to the right, stays the square root of x, but the bottom curve has now changed to this line. So functions of x, partitioning along the x-axis, would actually mean two integrals. Whereas, in this case, if I partition along the y, and I look at, in this case, the right curve is always the line, and the left curve as a function of y would always just be that parabola g of y equals y squared. So this would be one where it would make more sense to go with the y. So just kind of some things to think about there. All right, one last example, and we'll kind of set it up and see maybe which way makes more natural sense to us. So it says we are supposed to find a value of a such that the line, vertical line, x equals a number, so x equals a, divides the region bound by the graphs y squared equals 4 minus x and x equals 0. So that is my y-axis, x equals 0, the vertical line there. It divides it equally. So, this one, they haven't really given anything away. Everything's not given as a function of x or as a function of y. This y squared equals 4 minus x. I mean, if I want to solve it for y, I would have to introduce both the plus and minus square root if I'm trying to get like a graph of this in my graphing calculator. If I wanted to just try to sketch this function by hand, it's definitely going to be a parabola that's going to open in the horizontal direction. And you could maybe, just with that knowledge, plot some points. Like if you sub in your 0 for x, y squared equals 4. So y would be plus or minus 2. So you would now know that it would cross the y-axis here at plus and minus 2. What happens then if you subbed in 0 for the y? Oh, well, that would tell you that x would equal 4. And pretty quickly, just maybe by even just plotting those points, or by using your graphing calculator and entering the square root of 4 minus x and the minus square root of 4 minus x, we pretty quickly get our region here. So the region that we're looking at is we're trying to figure out, where should this x equals a be? So let's just kind of, not necessarily, so just, some value of a in here. So for some value at x equals a, such that the area of, let's say, this region in blue needs to equal, and so this is probably not drawn perfectly by any stretch of the imagination, has to equal this area in green. So I want those two areas to be equal. So I want, basically the blue area to equal the green area. Okay, so because I have symmetry here, I could focus on it in just the first quadrant. So let's just add that and say, because of symmetry, we could really just look at the blue area in quadrant 1, and that has to equal the green area in quadrant 1. So we can really just kind of focus in on that region. Okay, so with that, I think really either, since especially I'm restricting it to quadrant 1, I think really either type of setup, functions of x or functions of y, would be okay here, as we focus on what's happening up here just in that first quadrant. So if we think about this as a function of x, this top curve here is going to be our y equals the square root of 4 minus x. So that's going to be our top curve, and that's all I really care about. The bottom curve, of course, would be the the square root of 4 minus x. Okay, so let's just kind of keep going with this. If we get to a point we feel like it seems way too difficult or something, we can always, maybe go with a different approach. So if I look at my blue area, well, the blue area would be the definite integral from 0 to a of the area under the curve. I'm just in the first quadrant. I mean, it's just going to be that square root of 4 minus x dx. If you want, you can say minus 0, but you don't need that, and that's really what you studied in Calc 1, just the area under the curve down to the x-axis. You just need that curve. All right, the green area then is going to be the area from a, definite integral, from a over to 4. And then that again is just the square root of 4 minus x dx. So I just need those two to be equal. I think this looks pretty good because it's the same integral. I like the look of that. So maybe just kind of off to the side here. So let's just kind of go off to the side and take a look at what this integral of 4 minus x to the 1/2 dx would be. So this requires a u substitution. So we're doing a couple of basic u subs here. I would strongly recommend that you go back and kind of study your u sub if it's been a while. It's really important as we get started here. So u is going to be that 4 minus x. That means du is this negative dx. So if you divide by the negative, then you end up with negative du equaling the dx. And so that's going to be right there. So there's my negative du portion. All right, so what do we have here? We have the integral of, and what we had was this u to the 1/2, and the dx together is replaced with a negative du. So when we take our antiderivative, we get negative gets carried along. U to the 1/2 plus 1 would be u to the 3/2, dividing by 3/2, so multiplying by 2/3, and then replacing that with what u was originally, which was that 4 minus x. Okay, so that is going to be, just kind of go off to the side since they're both going to be the same. That is going to be our value there. All right, so bringing it back in, we have on the left-hand side here, we have our negative 2/3, and maybe we just think of this as the square root of 4 minus x cubed, since we're going to have to sub in a and 0. And so subbing in the a, we're going to have negative 2/3, our square root of 4 minus x, 4 minus a, I meant to say. We're subbing in the a, 4 minus a cubed, and then minus the negative, so plus 2/3. And then here we're going to have subbing in 0. The square root of 4 is 2, and 2 cubed is going to be 8. So that's the main reason I did that, was just it made it a little easier to think about that arithmetic. Okay, on the right-hand side of this equation, again, we have our antiderivative, negative 2/3, and then the square root of 4 minus x cubed, or you can just leave it as the 3/2. And then now subbing in between our limits of integration, subbing in the 4, that's going to give me 0, but the minus will still be there when I sub in the a, and then minus that negative 2/3, we'll change it into plus 2/3, and then the square root of 4 minus a cubed. So we are looking for where those two are equal. And so honestly, this doesn't look so bad really, right? Let's get our variable terms together over here on the right-hand side. So I'm going to add that term from the left over to the right-hand side. And so on the left-hand side, I just have my 16/3, and I have 2/3 plus another 2/3 of the same term. So those are like terms. So that's really 4/3 times that. Again, you can leave it as a square root. I might at this point just go back to 4 minus a to the 3/2. And obviously if you multiply both sides by 3/4 times that reciprocal here, so just multiplying both sides by the 3/4, you're just going to end up with 4 on the left-hand side equals your 4 minus a to the 3/2 power. Be careful that your a's do not start to look like 9s. Happens a lot. Okay. And so now let's raise both sides to the 2/3 power. If we left it like it was before, we could have taken the cube root and then squared it, but this is kind of why I went back to this. Looks a little nicer. So to the 2/3 power. And so that's not a nice perfect squaring or perfect cube, because that's like the cube root squared. So I'm just going to leave that as 4 to the 2/3. But then that gives us our 4 minus a there, because powers to powers you multiply, and that would just be to the first power. And so if we add the a to the left and then subtract the 4 to the 2/3 to the right, here's what we get. 4 minus 4 to the 2/3. And if you sub that into your calculator, it is approximately 1.48. So that would be where we would have that vertical line that would evenly distribute the green area to equal the blue area.